Hello everyone. Today, let's continue with elementary number theory. In the beginning of the class, let's look at the following theorem first. Let a, b, m be integers with m greater than 0. If a is congruent to b mod m, then a and b have the same remainder when being divided by m. I mentioned this a couple times in class, but I never give you a proof. Today, let's prove it. If a congruent to b mod m, then a and b have the same remainder when being divided by m. Let's prove it. Let R1 and R2 be the remainders. When a and b are divided by m respectively. Then, since R1 and R2 are the remainder, then there exists Q1. There exist integers Q1 and Q2. Such that a equal to Q1 times m. Here m is a divisor. A equal to Q1 times m. M is a divisor. Plus the remainder R1. Since R1 is a remainder, R1 must be between 0 and m. R1 cannot be the same as m, but R1 could be 0. R1 is between 0 and m. R1 must be strictly less than m, but R1 could be 0. And b equal to Q2 times m. Here m is a divisor. R2 is a remainder. And R2 is also between 0 and m since it's a remainder. A remainder must always be less than a divisor. Next, since a congruent to b mod m, then I can substitute Q1m plus R1 for a and Q2m plus R2 for b. If I plug in, I get Q1m plus R1 congruent to Q2m plus R2 mod m. Then a property of congruence says I can add any multiples of m to either side, either left side or right side. I can add any multiple of m to either side of this congruence. So I can add negative Q1m to both sides, to the left side, and add negative Q2m to the right side. I can add any multiples of m to either side of the congruence. This property says I can add any multiples of m to either side of this congruence. So I add negative Q1m to the left side, add negative Q2m to the right side. So I have R1 congruent to R2 mod m. R1 congruent to R2 mod m. That means m divides R1 minus R2. M divides R1 minus R2. So mk equal to R1 minus R2. So mk, m times this integer, m times integer k equal to R1 minus R2, where k is the integer. If m divides R1 minus R2, then m times integer k equal to R1 minus R2. Next, we know that R1 is between 0 and m. R2 is between R1 and R2, they are both between 0 and m. If I multiply these two equations, I leave the first equation the same. R1 is between 0 and m. If I multiply the second equation by -1, what do we get? If I multiply the second equation by -1, I have negative R2 here. If I multiply inequality by -1, the inequality sign will be switched. If I multiply inequality by -1, the inequality sign will be switched. It will be -m is less than -R2, which is less than 0. Then if I add inequality together, I have -m is less than R1 minus R2 less than m. So R1 minus R2 is between -m and m. If I add inequality, left side to the left side, middle to the middle, right side to the right side, I have -m is less than R1 minus R2 less than m. Since R1 minus R2 is between -m and m, since R1 minus R2 is between -m and m, then I can plug in mk. I can plug in mk for R1 minus R2. So mk is between negative m and positive m. Then, since m is a number greater than 0, since m is greater than 0, I can divide all three parts by m. Since m is a positive number, I can divide all three parts by m. So -1 is between -1 is less than k and is less than 1. Since k is an integer, and k is between -1 and 1. Since k is an integer and k is between -1 and 1, then the only integer between -1 and 1 is 0. Then k must be 0. Since k is an integer and k is between -1 and 1, the only integer between -1 and 1 is 0. Then k must be 0. Since k is 0, then R1 minus R2 must be 0. So R1 minus R2 equal to mk must be 0. Since k is 0, R1 minus R2 equal to mk, it must be 0. Hence, R1 must be the same as R2. Hence, R1 must be the same as R2. That means the remainder of A and B must be the same when they are divided by m. The remainder of A and B must be the same when they are divided by m. Since R1, R2 are the remainders. Let's complete the proof. Next, let's do an example. Let m be an integer with n greater than or equal to 100, and let a be an integer represented by the last two digits of n. Show that m and a have the same remainder when being divided by number 4. So, what does this problem mean? A is an integer, n is an integer greater than or equal to 100. A is an integer represented by the last two digits of n. What does it mean? For example, n is 2978. A is an integer represented by the last two digits of n. The last two digits of n is 78 here. So A is 78. A is an integer represented by the last two digits of n. That's one example. Another example, if n is 23,759, then A is an integer represented by the last two digits of n. This is the last two digit of n. So here A is 59. If n is 315,228, then A is a number represented by the last two digits of n. Here A is 28. A is always the number represented by the last two digits of n. That's what it means. And this problem says n and a have the same remainder when being divided by 4. That means if I take n divided by 4 and a divided by 4, they must have the same remainder. If I take for each pair here, if I take n divided by 4 and a divided by 4, I must have the same remainder for every pair. That's what this problem says. Let's prove it. How can we prove that n and a have the same remainder when being divided by 4? So first of all, keep one idea in mind. N can always be written as 2900 plus 78. That's 100 times 29 plus 78. So n can always be written as, this is a. Let me call this number b. So n, in every case here, n can always be written as 100b plus a, where b is another integer. N can always be written as 100 times an integer b plus a, where b is another integer. It works for every case here. For example, in the second case, a can be written as 23,700 plus 59. That can be rewritten as 100 times 237 plus 59. This is a. I can call this number b. So n can always be rewritten as 100b plus a, where b is an integer. It works for every case. So n can always be written as 100b plus a, where b is an integer. So let n be an integer with n greater than or equal to 100. And let a be the integer represented by the last two digits of n. Let a be the integer represented by the last two digits of n. Then n can always be written as 100 times b plus a, where b is another integer. Next, this equation can be rewritten as n minus a equal to 100b. This equation, if I bring a over, it can be rewritten as n minus a equal to 100b. And 100b can be rewritten as 4 times 25b. Since b is an integer, 25b is another integer. Since b is an integer, 25b is also integer. So we have 4 divides n minus a. So 4 divides n minus a. So by the definition of congruence, we know that n congruent to a must 4. So n congruent to a must 4. Then by the previous theorem, since these two numbers n congruent to a, then by the previous theorem, if a congruent to b must m, then a and b have the same remainder when being divided by m. So here, since a congruent to b my m. Then by the previous theorem, n and a have the same remainder when being divided by 4. So by the previous theorem, n and a have the same remainder when being divided by 4. So that's the proof of this theorem. Now, let's observe this theorem for one thing. If 4 divides a, then we can say that four divides a minus 0. So we have a congruent to 0, mark 4. And since n congruent to a, we also have n congruent to 0, mark 4. Hence, 4 divides m minus 0, and hence 4 divides n. So here we can say that if 4 divides a, then 4 also divides n. If a is divisible by 4, then n is also divisible by 4. So keep this, let me write this in words. Let n be an integer. If the number represented by its last 2 digits is divisible by 4, then n itself is divisible by 4. Let me put the last sentence here. Then n itself is divisible by 4. So if n is an integer, if the number represented by its last 2 digits, so a is a number represented by its last 2 digits. If the number represented by its last 2 digits is divisible by 4, that means 4 divides a, then n itself is also divisible by 4. Then n itself, 4 also divides n, that means n itself is divisible by 4. So keep this idea in mind. If n, let n be an integer. If the number represented by its last 2 digits, if the number represented by its last two digits is divisible by 4, then n itself is divisible by 4. So if we have a very, very large number, say 23,000, say 798 and 144, we want to know if this number is divisible by 4. How can we do? If we divide the entire number by 4, it may be too much work. We can just verify the last 2 digits. If the number represented by its last 2 digits is 44, we can simply verify 44. If 4 divides 44, then we can say 4 divides the entire number. If 4 doesn't divide 44, then 4 doesn't divide this entire number. So for a very, very large number, for divisibility of 4, we can simply verify the last two digits. If the last two digit is divisible by 4, then the number itself is divisible by 4. The same rule works for number A. The same rule works for number A. The proof is very similar. Here I don't prove it here, but the same rule works for number A. Note, the same rule works for number A. Proof is very, very similar. I don't prove it here. You can verify by yourself. Let m be an integer. If the number represented by its last 3 digits is divisible by A, then the number n itself is also divisible by A. The proof is very similar as the previous statement. The proof is very similar as the previous statement. Next example, let m be a positive integer and let a be the sum of its digits. Show that n and a have the same remainder when being divided by 9. What does this problem mean? What does it mean? The sum of the digits. For example, if n is 279, the sum of the digits is 2 plus 7 plus 9. If n is 279, the sum of the digits is 2 plus 7 plus 9, which is 18. Another example, if n is 3412, the sum of the digits is 3 plus 4 plus 1 plus 2, which is 10. If n is 52,722, the sum of the digits is 5 plus 2 plus 7, that's 14. 14 plus 2 plus 2, that's 18. That's the sum of the digit. And this theorem says, let m be a positive integer and let a be the sum of its digit. Then n and a have the same remainder when being divided by 9. That's what this theorem says. Now let's try to prove it. Before we prove it, let me show you one thing. 279, it can be written as 200 plus 70 plus 9, which means 2 times 100 plus 7 times 10 plus 9 times 1. It can be written as 2 times 10 squared, 7 times 10 to the power 1 plus 9. I can write 1 as 10 to the power 0. And 3,412. It can be written as 3,000 plus 400 plus 10 plus 2. This can be rewritten as 3 times 1,000 plus 4 times 100 plus 1 times 10 plus 2 times 1. 1,000 can be written as 10 to the power of 3. 100 can be written as 10 to the power of 2. Number 10 is 10 to the power of 1. We can consider number 1 as 10 to the power of 0. This is called the decimal expansion of 3,412. This is called a decimal expansion of 3412. And this is called a decimal expansion of This is called a decimal expansion of 279. This is called a decimal expansion of 279. So keep this idea in mind. We'll use this idea to prove this statement here. Now let's prove it. Let n be a k-digit number with digits ak minus 1, ak minus 2, a2, a1, a0. Let n be a k-digit number with digits ak minus 1, ak minus 2, a2, a1, a0. From a0 to ak minus 1, they are k digits. From a0 to ak minus 1, they are k digits. For example, for this number 3412, we call this a0, call this a1, call this a2, and call this a3. That's a 4-digit number. From a0 to a3, that's a 4-digit number. And this is a 5-digit number. I can call this a0, the digit here is a0, a1, a2, a3, a4. If this is a 5-digit number, the digit is from a0 to a4. If this is a 5-digit number, the digit is from a0 to a4. If this is a 4-digit number, the digit is from a0 to a3. So similarly, if n is a k-digit number, the digit is from a0 to ak minus 1. From a0 to ak minus 1, they are k digits. Then let ak minus 1 times 10 to the power of k minus 1 plus ak minus 2 times 10 to the power of k minus 2 plus a2 times 10 squared plus a1 times 10 plus a0. Then this be the decimal expansion of n. Then this be the decimal expansion of n. Then we have n equal to ak minus 1 10 to the power of k minus 1 plus ak minus 2 times 10 to the power of k minus 2 plus a squared a sub 2 times 10 squared plus a sub 1 times 10 plus a0. So then this be the decimal expansion of n. For example, for 279, I let this be the decimal expansion of 279. If n is 3412, I let this be the decimal expansion of 3412. This is a0, number 2 is a0, number 1 is a1, number 4 is a2, and number 3 is a3. This is called decimal expansion. a3 times 10 to the power of 3, a2 times 10 to the power of 2, a1 times 10 to the power of 1, and a0 times 10 to the power of 0. So a sub k minus 1 times 10 to the power of k minus 1, a sub k minus 2 times 10 to the power of k minus 2, plus a sub 2 times 10 squared, plus a sub 1 times 10 to the power of 1, plus a sub 0 times 10 to the power of 0. 10 to the power of 0 is 1. So this is the decimal expansion of n. Next, we know that Number 1 congruent to itself, mod 10. Number 1 congruent to itself, mod 10. Sorry, mod 9. We try to show divisibility of 9. Number 1 congruent to itself, mod 9. How about number 10? How about number 10? 10 divided by 9. What's the remainder? 10 congruent to what? Mod 9. If we take the remainder, 10 divided by 9, remainder is 1. If I take the remainder, 10 divided by 9, remainder is 1. Then how about 10 squared? By a theorem we learned last class, if 10 congruent to 1, I can raise both sides to the power of 2. If 10 congruent to 1, mod 9, I can raise both sides to the same power. Here I raise both sides to the power of 2. So 10 squared congruent to 1 squared, mod 9. And in general, 10 to the power of k minus 2. If I raise both sides to the power of k minus 2, 1 to the power of k minus 2 is 1. Mod 9. So here we can see that 10 raised to every power congruent to 1, mod 9. And 10 to the power of k minus 1 also congruent to 1, mod 9. Next, in the first equation, if I multiply both sides by a0, if I multiply both sides by a0, I have a0 congruent to a0, mod 9. In the second equation, if I multiply both sides by a1, I have a1 times 10 to the power of 1 congruent to a1, mod 9. If I multiply both sides by a1, I have a1 times 10 to the power of 1 congruent to a1, mod 9. If I multiply, in the third row, if I multiply both sides by a2, I have a2 times 10 squared congruent to a2, mod 9. Continue here for 10 to the power of k minus 2 congruent to 1, mod 9 here. If I multiply both sides by a sub k minus 2, then I have a sub k minus 2 times 10 to the power of k minus 2 congruent to a sub k minus 2, mod 9. In the last row here, if I multiply both sides by a sub k minus 1, I have a sub k minus 1, 10 to the power of k minus 1, congruent to a sub k minus 1, mod 9. Now next, in this part here, since they are all congruent, if I add the left side together and add the right side together, they are still congruent, mod 9. Since they all congruent, every linear congruent here, they congruent to each other. Here, every statement here, they congruent to each other. If I add the left side together and add the right side together, they still congruent to each other, mod 9. If I add the left side together and add the right side together, they still congruent to each other, mod 9. Now, if I add the left side together, what do we get? If I add the left side together, what do we get? If I add the left side together, I have a0 plus a1 to the power 1 plus a2 to the power of 2 plus a sub k minus 2 10 to the power of k minus 2 plus a sub k minus 1 times 10 to the power of k minus 1. That's the left side. If I add the left side together, that's the left side. Let me write them closer. If I add the left side together, I have a0 plus a1 times 10 plus a sub 2 times 10 squared plus a sub k minus 2 times 10 to the power of k minus 2 plus a sub k minus 1 times 10 to the power of k minus 1. Congruent to the right side here. The right side of the congruence here is a0 plus a1 plus a2 plus a2 minus 1 plus ak minus 1, ak minus 2, ak minus 1. So if I add the right side together, I have a0 plus a1 plus a2 plus ak minus 2 plus ak minus 1 mod 9. So if I add the left side and the right side, they still congruent to each other, mod 9. Now what's the left side? Left side is the decimal expansion of n. Left side is the decimal expansion of n. So left side actually equal to n. What's the right side? What's the right side here? a0 plus a1 plus a2 plus ak minus 2, ak minus 1. What's the right side here? That's the sum of the digits, because the digit is ak minus 1, ak minus 2, a2, a0, a1. The right side here is the sum of the digits, and we know a is the sum of the digits. A is the sum of the digits. So n congruent to a mod 9. N congruent to a mod 9. So let's complete the proof. So n congruent to a mod 9. By the previous theorem, by the first theorem we did today. Since n congruent to 9, n congruent to a mod 9, that means n and a have the same remainder. When being divided by 9. By the first theorem we did today, n congruent to a have the same remainder when being divided by 9. Now let's complete the proof. Next, let's observe one thing. If 9 divides a, then what can we say about n? Let's observe one thing. If 9 divides a, then what can we say about n? 9 divides n, that means nine divides a minus 0. I can write a as a minus 0. So if 9 divides a minus 0, so I can say a congruent to 0 mod 9. I can say a congruent to 0 mod 9. Since n congruent to a mod 9 and a congruent to 0 mod 9, then I can say n congruent to 0 mod 9. Since n congruent to a congruent to 0, I can say n congruent to 0 mod 9. So n9 divides m minus 0. By the definition of congruence, 9 divides m minus 0. By the definition of congruence, 9 divides m minus 0. And I can say 9 divides n, because m minus 0 is n. So here we can see that if 9 divides a, then 9 divides n. If 9 divides the sum of the digits, if 9 divides the sum of the digits, because a is the sum of the digits, because a is the sum of the digits. If 9 divides the sum of the digits of a number, then 9 divides the number itself. So keep this idea in mind. Note: let n be an integer. If the sum of the digits in n is divisible by 9, then n itself is also divisible by 9. N itself is also divisible by 9. If the sum of digits in n is divisible by 9, if the sum of the digits in n is divisible by 9, then n itself is also divisible by 9. If the sum of the digits in n is divisible by 9, then n itself is also divisible by 9. For example, for this number here, 279. If the sum of the digits is 18, if 18 is divisible by 9, then this number is also divisible by 9. And for this number, 3412, the sum of a digit is 10. If 10 is not divisible by 9, then this number itself is not divisible by 9. And for this number, 52,722, if the sum of a digit is divisible by 9, then this number is also divisible by 9. So dividing the sum is much easier than dividing the number itself. If we try to divide this number by 9, it may take much longer. But if we divide the sum of the digit by 9, it's much easier. So if for any integers, if the sum of a digit is divisible by 9, then the number itself is also divisible by 9 by this statement. And the same idea also works for number 3. The proof is very, very similar. The same idea works for number 3. The proof is very, very similar. Yeah, I don't prove it here, but let me give you a statement. I don't give you proof here. The proof is very similar as this statement. I don't give you proof here, but let me give you the statement. The same idea works for number 3. Let m be an integer. If the sum of the digits in n is divisible by 3, then n itself is also divisible by 3. Next, let me introduce the least non-negative residue. Least non-negative residue. Usually we write L and R represent the least non-negative residue. Let A, R, and M be integers. With M is greater than 0. Let A, R, and M be integers with M is greater than 0. If A congruent to R, if A is congruent to R, mark M. If A is congruent to R, mark M. And R is between 0 and M. R could be 0, but R must be strictly less than M. Then R is called the least non-negative residue of M, of A. R is called the least non-negative residue of A. If A congruent to R, mark M, and R is between 0 and M, R could be 0, but R must be strictly less than M, then R is called the least non-negative residue of A. Note: keep this idea in mind. If R is the least non-negative residue of A, then R is also the remainder. If R is the least non-negative residue of A, then R is also the remainder. When A divided by M. If R is the least non-negative residue of A, then R is also the remainder when A is divided by M. Keep this idea in mind. Keep this idea in mind. Next, let me show you some examples. Find the least non-negative residue of 16. Mark 5. Find the least non-negative residue of 16. Mark 5. So to find the least non-negative residue, we can try to take the remainder. To find the least non-negative residue of 16, mark 5, we try to take remainder. If I take 16 divided by 5, what's the remainder? 16 divided by 5, remainder is 1. So this is the least non-negative residue. Next. Find the least non-negative residue of 29. Mark 6. Find the least non-negative residue of 29. Mark 6. (29) congruent to what number? Mark 6. 29 congruent to what number? Mark 6. Take remainder. If we try to find the if we try to find the least non-negative residue, we try to take remainder. 29 divided by 6, remainder is 5. So that's the least non-negative residue. Find the least non-negative residue of A, Ma12. Find the least non-negative residue of A, Ma12. A congruent to what, Ma12? A congruent to what number, Ma12? If I take A divided by 12, the remainder is A itself. Since A is less than 12, if I take A divided by 12, the remainder is A itself. So for number A, since A is less than 12, the least non-negative residue of A is number A itself. Find the least non-negative residue of negative 19 minus 3. Find the least non-negative residue of negative 19 minus 3. What can we do here? Negative 19 congruent to what, minus 3? So for negative 19, we can do this. Ignore the negative sign first. If we take 19, if we take positive 19 divided by 3, what's the remainder? If we take positive 19 divided by 3, what's the remainder? If we take positive 19 divided by 3, what's the remainder? (19) divided by 3, the remainder is 1. So if I multiply both sides by negative 1, negative 9 will congruent to negative 1 minus 3. If I multiply both sides by negative 1, negative 19 will congruent to negative 1 minus 3. But this number must be non-negative. And we know that for linear congruence, I can add one side by any multiple of number 3. I can add one side of the congruence by any multiple of 3. So if I add 3 here, it stays the same. The congruence stays the same. Negative 19 congruent to 2 minus 3. Now this number is positive and it's less than 3. This number is non-negative and it's less than 3. So number 2 is the least non-negative residue of negative 3, of negative 19 minus 3. So number 2 is the least non-negative residue of negative 19 minus 3. Next example. Solve for x. S congruent to 32 minus 9. S congruent to 32 minus 9. This is called a congruence. This is not equation. This is called congruence. When we solve congruence for x, note, when we are solving congruence for x, we need to get x by itself on the left side, which means isolate x on the left side. When we are solving congruence for x, we need to isolate x on the left side, get x by itself on the left side. And x, for the final answer in the simplest form, x must be congruent S must be congruent to a least non-negative residue mod M. X must be congruent to a least non-negative residue mod M. For the answer in the simplest form of two things, we need to get x by itself on the left side, and x must be congruent to a least non-negative residue of M. Now here we already get x by itself on the left side. Is this number the least non-negative residue mod 9? Is this number the least non-negative residue of mod 9? This number is more than 9. This number is more than 9, so we know this is not a least non-negative residue of 9. How do we find the least non-negative residue? We find the remainder. Take 32 divided by 9, find the remainder. 32 divided by 9, remainder is 5. And we know that 5 is less than 9. So 5 must be a least non-negative residue of 9. 5 is positive and is less than 9. 5 must be a least non-negative residue of 9. Here we get x by itself, and 5 is a least non-negative residue. We are done. And also one more step. We are solving for x. For the final answer, we need to write x equal to something, not congruent to something. For the final answer, we need to write x equal to some number. For the final answer, we need to write x equal to some number, not congruent, not x is congruent to some number. We must write x is equal to some number. Now how do we make an equation here? How do we make an equation here? Keep this idea in mind. If x is congruent to 5 mod 9, what does it mean? If x is congruent to 5 mod 9, what does it mean? It means 9 divides x minus 5. What does 9 divides x minus 5 means? 9 divides x minus 5. It means 9 times the integer t equal to s minus 5, where t is the integer. 9 divides s minus 5. That means 9 times the integer t equal to s minus 5, where t is the integer. If we try to get s by itself, if we try to solve this equation for x, s can be written as 5 plus 9t. I can bring 5 over. S equal to 9 plus 5t. T is the integer. So this congruence, x congruent to 5 mod 9, can be rewrite as x equal to 5 plus 9t, where t is the integer. That's how we solve for x. When we solve for x, we must write x equal to some number. So the final answer, x equal to 5 plus 9t, where t is the integer. That's how we write x. For example, t could be any number. T could be 0. When t is 0, x is 5. When t is 1, x is 14. T could be any number. When t is 2, x is 23. S could be any number in the form of 5 plus 9t, where t can be any integers. That's how we solve for x. When we solve for x, we need to get x by itself. Write it as an equation, s equal to something. And this number here must be the least non-negative residue. Next. X congruent to negative 27 mod 11. X congruent to negative 27 mod 11. So if this number is negative, we can also divide final remainder. We know that positive 27 divided by 11, remainder is 5. So negative 27 divided by 11, remainder is negative 5. But negative 5 is not the least non-negative residue. Negative 5 is not the least non-negative residue. So here, to make it positive, I can add 11 here. For congruence, I can add any multiple of 11 to either side. Let me add 11 here. Then x congruent to 6 by 11. 6 is non-negative, and 6 is less than 11. This is a least non-negative residue by 11. So for the final answer, you can write x equal to 6 plus 11t, where t is an integer. If you run an answer like this, it should be okay. But to make the computation easier later, I suggest this form. If you run an answer like this, it should be okay. As long as this number, as long as you get x by itself, and this number is the least non-negative residue, that's okay. That should be okay. So either way is okay. But for the future calculation, I prefer you run answer in this form. For your future computation, I suggest you run answer in this form. Answer in this form should be okay. As long as you get x by itself and it's congruent to a least non-negative residue by 11, that should be okay. But for your future computation, I suggest you run answer in this form. Run answer as an equation. I suggest you run answer as an equation. S congruent to 529. Mod 15. S congruent to negative 529 mod 15. What can we do here? This number is negative. We need to first of all find a remainder. We cannot divide negative number to find a remainder. So let's divide positive 529 by 15 and find a remainder. Let's take positive 529 divided by 15 and take a remainder first. (529) divided by 15. 15 goes into 79 5 times. 5 times 15 is 75. Remainder is 4. So 529, positive 529 divided by 15, remainder is positive 4. That means negative 529 divided by 15, remainder will be negative 4 mod 15. In order to make it positive, I add 15 here. So I have x congruent to 11 mod 15. This number is less than 15 and it's non-negative, so that's okay. We get x by itself, and this number here is the least non-negative residue of 15, so that's okay. That's an acceptable answer. And I suggest you run answer as an equation. X equal to 11 plus 15t, where t can be any integers. S equal to 11 plus 15t, where t can be any integers. Either way is okay. But for your future computation, I suggest you run the answer in this form. Next, let me introduce modular inverse. Let a, b, and m be integers. Let a, b, and m be integers with m greater than 1. If a times b is like b times a, if b times a congruent to 1 mod m, if b times a congruent to 1 mod m, then b is called a modular inverse of a. Then b is called a modular inverse of a. denoted by inverse of A congruent to B my M. B is called the inverse of A. B is called the inverse of A, denoted by inverse of A congruent to B my M. Now, let's do some simple example. Find the inverse of 4 mod 5. Find the inverse of 4 mod 5. How do we find the inverse of 4 mod 5? So, in order to find the inverse, we try to find some integer times 4 congruent to 1 mod 5. In order to find the inverse of 4 mod 5, we try to find some integer times 4 congruent to 1 mod 5. We try to find some integer times 4 congruent to 1 mod 5. Here we can try the numbers. If I put 1 here, 1 times 4 is 4. 4 divided by 5, remainder is not 1. If I put 2 here, 2 times 4 is 8. 8 divided by 5, remainder is 3, which is not 1. So 2 doesn't work. If I try 3 here, 3 times 4 is 12. 12 divided by 5, remainder is 2, which is not 1. So 3 won't work. Or if I try 4, 4 times 4 is 16. 16 divided by 5, remainder is 1. So 4 works. So 4 works. That means number 4 is the inverse of 4. So we say the answer. Inverse of 4 is 4 mod 5. So inverse of 4 is 4 mod 5. Inverse of 4 is 4 mod 5 because 4 times 4 congruent to 1 mod 5. 4 times 4 is 16. 16 divided by 5, remainder is 1. So this 4 is the inverse of 4. The number in front of x, coefficient in front of A, is called the inverse of A. The coefficient in front of A is called the inverse of A. So since 4 times 4 congruent to 1 mod 5, we say inverse of 4 is 4 mod 5. Another example. Find the inverse of 3 mod 7. Find the inverse of 3 mod 7. How do we find the inverse of 3 mod 7? We try to find some number times 3 that is congruent to 1 mod 7. We try to find some number, some integer that times 3 congruent to 1 mod 7. How do we find inverse of 3? We can try some numbers. If I plug in 1 here, 1 times 3 is 3. 3 divided by 7, remainder is 3. It won't work. 1 won't work. If I try 2, 2 times 3, 2 times 3 is 6. 6 divided by 7, remainder is 6, which is not 1. So 2 won't work. If I try 3, 3 times 3 is 9. 9 divided by 7, remainder is 2, which is not 1. So 9 won't work. So 3 won't work. If I try 4, here, 4 times 3 is 12. 12 divided by 7, remainder is 5. So 4 won't work. If I try 4 here, 4 times 3 is 12. 12 divided by 7, remainder is 5, which is not 1. It won't work. Or if I try 5, What if I try 5? 5 times 3 is 15. 5 times 3 is 15. 15 divided by 7, remainder is 1. So 5 works. So the answer, we say inverse of 3 is 5 mod 7. Inverse of 3 congruent to 5 mod 7. Since 5 times 3 is 15. 15 divided by 7, remainder is 1. So inverse of 3 is 5. The coefficient in front of A is inverse of A. The coefficient in front of A is inverse of A. Next. Find the inverse of 4 mod 6. Find the inverse of 4. Inverse of 4 mod 6. How do we find inverse of 4 mod 6? We try to find some integer times 4 that congruent to 1. That is congruent to 1 mod 6. We try to find some integer that times 4 congruent to 1 mod 6. Let's try. If I try 1, 1 times 4 is 4. 4 divided by 6, remainder is 4. It's not 1. 1 won't work. Or if I try 2, 2 times 4 is 8. 8 divided by 6, remainder is 2. So 2 won't work. What about 3? 3 times 4 is 12. 12 divided by 6, remainder is 0, which is not 1, so it won't work. What about 4? 4 times 4 is 16. 16 divided by 6, remainder is 4. It won't work. So it looks like we try many numbers. We cannot find an answer here. It looks like we try many answers. We cannot find an answer. We cannot find an inverse. Here, we are not able to find an answer here. We try many numbers, and we are not able to find an answer. Here we try many numbers, and we see that we are not able to find an answer. Now my next question is, under what condition we have solution? Under what condition we are able to find an answer? Under what condition we are not able to find an answer? You see that in example 1 and 2, we try and get 2 answers. In example 3, no matter how we try, we are not able to find an answer. My next question is, under what condition we are able to find an answer? We are able to find an inverse. Under what condition we are not able to find an inverse? So look at the following theorem. The following theorem will tell you under what condition we can find an inverse, and under what condition we are not able to find an inverse. Let A and M be integers with m greater than 1. The modular inverse of A mod m exists if and only if the GCD of AM is 1. So the modular inverse of A mod m exists if and only if the GCD of AM is 1. In this example, this is A, this is M. We treat this as A, this is M. If the GCD of AM is 1, then the inverse exists. If the GCD of AM is 1, then the inverse exists. If the GCD of AM is not 1, if the GCD of AM is not 1, then the inverse does not exist. We are not able to find the inverse. GCD of 4 and 6 is 2, which is not 1. According to this theorem, we are not able to find the inverse. Now, let's prove the theorem. This theorem statement is something if and only if something else. For a statement in the form of P if only if Q, this is equivalent to P implies Q and Q implies P. So we need to prove in two directions. First of all, assume P, then prove for Q. Next, we assume Q and prove for P. We need to prove in both directions. First of all, assume P, then prove for Q. Next, we assume Q and then prove for P. We need to prove it in both directions. So let's prove it in both directions. First of all, let's assume P and prove for Q. Let's assume the modular inverse of A, mod M, exists. Assume the modular inverse of A, mod M, exists. Then there exists an integer b such that a times b times a congruent to 1 mod M. Assume the modular inverse of A mod M exists. Then there exists an integer b. This b is the inverse of A. There exists an integer b such that b times a congruent to 1 mod M. Then by definition of modular, by definition of congruence, I can write M divides BA minus 1. So I can write M divides BA minus 1, which means M times the integer K equal to BA minus 1. Where K is the integer. If I solve this equation for 1, what do we get? If I solve this equation for 1, I can write 1 equal to BA minus MK. If I solve this equation for 1, I can write 1 equal to BA minus MK. Next, we try to show that the GCD of AM is 1. Let D be the GCD of AM. We try to prove that D is 1. Let D be the GCD of AM. We try to prove that D must be 1. If D is the GCD of AM, then what do we have? Then D divides A. And D divides M. If D is the greatest common divisor of AM, then D must divide both numbers. So D divides A and D divides M. Hence, D divides any linear combination of AM. If D divides A, D divides M, then D divides any linear combination of AM. So D divides BA minus mk. If b divides a and b divides m, then b divides any linear combination of am. If b divides a, if d divides a, d divides m. D divides any linear combination of am with integer coefficients. Here b is an integer, k is also integer. So d divides any linear combination of am with integer coefficients. Hence d divides ba minus mk. Since ba minus mk is 1, since ba minus mk is 1, then we have d divides 1. So d is a factor of 1. Since the only factor of number 1 is number 1 itself, since the only factor of number 1 is number 1 itself, so d must be 1. Since the only divisor of 1 is number 1 itself, if d divides 1, then d must be 1. The only divisor of number 1 is number 1 itself. Since d divides 1, d must be 1. So the GCD of am equal to d, which is 1. So the GCD of am equal to d, which is 1. Here we prove q. We assume p and prove q. Now next, go back. Assume q, prove for p. Assume q and prove for p. For if and only if statement, for the statement of if and only if, we must prove in both directions. First of all, assume p implies q. Then assume q, try to prove for p. On the other direction, assume the GCD of am equal to 1. Assume the GCD of am equal to 1. We try to show that the modular inverse of a by m exists. We try to show that the modular inverse of a by m exists. So assume the GCD of am equal to 1. Then by Bezout theorem, I can write the GCD as a linear combination of am with integer coefficients. By Bezout theorem, I can write the GCD number 1 as a linear combination of am, s times a plus t times m, with integer coefficients, where s and t are integers. This is Bezout theorem. The GCD of am can be written as a linear combination of am with integer coefficients. Here s and t must be integers. Next, we know that 1 equal to s times a plus tm. This equation can be rewritten as sa minus 1 equal to negative tm. This equation can be rewritten as sa minus 1 equal to negative tm. Then sa minus 1 equal to m times negative t. Since negative t is an integer, since sa minus 1 equal to m times the integer, that means m divides sa minus 1. Since sa minus 1 equal to m times the integer, that means m divides sa minus 1. So s times a congruent to 1 my m. Here s times a congruent to 1 my m. Here we have s times a congruent to 1 my m. So s, this integer s is the inverse of a, since s is an integer. Since s is an integer, then s is a modular inverse of a. Since s is an integer, then this s is a modular inverse of a, my m. Here we prove p. Here we prove p. P says the modular inverse of a exists, and we find a modular inverse of a. That complete the proof here. That's p. So we assume q, prove p. Since we assume p improved and proved for q, and we assume q and prove for p, that complete the proof. The modular inverse of a, my m, exists if and only if the GCD of am equal to 1. Next, let me show you how to find the inverse of a, my m. Find the inverse of a, my m. First example, a equal to 7, m equal to 19. Find inverse of a, my m. So first of all, let's check. If the GCD of am is 1, then there exists inverse. If the GCD of am is not 1, then the inverse does not exist. What's the GCD of 7 and 19? We can use Euclidean algorithm to verify this. Take 19 divided by 7, larger divided by smaller. 19 divided by 7. 7 goes to 19 two times. 2 times 7 is 14. Remainder is 5. Replace the larger number with a smaller number. Then, for GCD of 7 and 5, keep dividing. Take larger number, divide by smaller number. 5 goes to 7 one time. 1 times 5 is 5. Remainder is 2. Then replace the larger number with a remainder. Next, keep dividing. Take larger number, divide by smaller number. 5 divided by 2. 2 goes to 5 2 times. 2 times 2 is 4. Remainder is 1. Then replace the larger number with a remainder. Next, keep dividing. Take larger number, divide by the smaller number. 1 goes to 2 2 times. 1 times 2 is 2. Remainder is 0. Then replace the larger number with a remainder. GCD of 0 and 1 is 1. Since the GCD of am is 1, we know that the inverse of a, my m, exists. Since the GCD of am is 1, we know that the GCD of am exists. Now, how do we find the inverse of a? According to the previous theorem, we know that if I can write 1 as a linear combination of am, if I write 1 as a linear combination of a and m, then the number in front of a is the inverse of a. The coefficient of a is the inverse of a. The number in front of a is the inverse of a. So if I can write 1 equal to some number times a plus some number times m. If I can write 1 as a linear combination of a and m with integer coefficients, then the number in front of m, the number in front of a, is the inverse of a. If I can write 1 as a linear combination of am with integer coefficients, then the integer in front of a is the inverse of a. So that's our goal. So in order to write 1 as a linear combination of am, we try to use the extended Euclidean algorithm. In order to write 1 as a linear combination of a and m, I try to use the extended Euclidean algorithm. So first of all, let's convert each division into an equation. Let's convert each equation into a division. First division here is 19 equal to 2 times 7 plus 5. Second equation, 7 equal to 1 times 5 plus 2. Third equation, 5 equal to 2 times 2 plus 1. And the fourth equation, 2 equal to 2 times 1 plus 0. We cross out the last row which ends with a 0. Cross out the last row which ends with a 0. For each row here, get the remainder by itself. I have 1 equal to 5 minus 2 times 2. 2 equal to 7 minus 1 times 5. And here 5 equal to 19 minus 2 times 7. Then try to substitute. Start from last row, try to substitute backward. Last row says 1 equal to 5 minus 2 times 2. I can first of all replace this 2 with the previous row. I get 1 equal to 5 minus 2 times 7 minus 1 times 5. Replace number 2 with the second row here. Then distribute and simplify. If I distribute 2, I get 2 times 7. Negative 2 times negative 1 is positive 2. 1, 5 plus 2, 5. 1, 5 plus 2, 5 is 3, 5. 1, 5 plus 2, 5 is 3, 5. Next, replace number 5 with the previous row. Number 5 is 19 minus 2 times 7. Then distribute number 3. I have 3 times 19 minus 6 times 7 minus 2 times 7. If I combine like terms, negative 6 times 7 plus negative 2 times 7 is negative 8 times 7. If I combine like terms, negative 2 times 7 plus negative 6 times 7 plus negative 2 times 7 is negative 8 times 7. Then the inverse of 7, we're looking for inverse of 7. The inverse of 7 is the number in front of 7, is the coefficient of 7. The inverse of 7 is the number in front of 7, which is negative 8. So here, we know that the inverse of 7 is negative 8 mod 19. The inverse of 7 mod 19 is negative 8. The coefficient in front of 7 is the inverse of 7. The inverse of A is the number in front of A. The number in front of A is the inverse of A mod M. By the previous theorem, we know that. Once I write 1 as a linear combination of A and M, the coefficient of A is the inverse of A. here our a is 7. The coefficient of 7 is negative a. The coefficient of 7 is negative a. So negative a is the inverse of 7. Negative a is the inverse of 7. Now, next, for the final answer, usually we try to use the least non-negative residue. Usually for the final answer, we try to use the least non-negative residue. Negative a is negative, and this number is less than 19. In order to make it positive, I can add 19 here. Remember, for congruence, I can add any multiple of 19. I can add any multiple of m to either side. Here, let me add 19 here. I have inverse of 7 congruent to 11 mod 19. So inverse of 7 congruent to 11 mod 19. How do we check the answer? How do we check the answer? How do we check? 11 is the inverse of 7. How do we check? 11 is the inverse of 7 mod 19. How do we check? So in order to check 11 is the inverse of 7 mod 19, we take 11 times 7, then divide by 19. We take 11 times 7, then divide by 19. If the remainder is 1, then 11 is the inverse of 7. Let's check. If I take 11 times 7, I get 77. Then take 77 divided by 19. We know that 19 goes into 77 4 times. 4 times 19 is 76. Remainder is 1. If the remainder is 1, then inverse of 7 is 11. If the remainder is 1, that means 11 is the inverse of 7 mod 19. Next example. A equal to 13. M equal to 61. Find the inverse of A mod M. Find the inverse of A mod M. What should we do first? First of all, we need to check the GCD. First of all, check the GCD. If the GCD of 13 and 61 is 1, then the inverse of A exists. Inverse of A mod 13, inverse of A mod M exists. But if the GCD of A and M is not 1, if the GCD of A and M is not 1, then the inverse of A mod 61 does not exist. So let's check GCD first. Let's use Euclidean algorithm. Take larger number, divide by the smaller number. 61 divided by 13. 13 goes into 61 4 times. 4 times 13 is 52. 61 minus 52 is 9. So the remainder is 9. Replace the larger number with the remainder. Next, keep dividing. Take larger number, divide by smaller number. 13 divided by 9. 9 goes into 13 1 times. 1 times 9 is 9. Remainder is 4. Then replace a larger number with the remainder. Next, keep dividing. Take larger number, divide by smaller number. 4 divided by 9. 4 goes to 9 2 times. 2 times 4 is 8. Remainder is 1. Then replace a larger number with the remainder. Next, keep dividing. Use larger number, divide by smaller number. Take 4 divided by 1. 1 goes into 4 4 times. 4 times 1 is 4. Remainder is 0. Then replace a larger number with a remainder. Replace a larger number with a remainder. GCD of 0 and 1 is 1. GCD of 0 and 1 is 1. Since the GCD of AM is 1, then we know that inverse of A exists. Inverse of A mod M exists. Now how do we find inverse of A? In order to find inverse of A, we try to write 1 as the linear combination of AM. If I write 1 as the linear combination of AM, then the coefficient of A is the inverse of A. The number in front of A is the inverse of A. So let's try to apply the extended Euclidean algorithm. Let's first of all rewrite each division as an equation first. 61 61 equal to 4 times 13 plus 9. Next division, 13 equal to 1 times 9 plus 4. Next division, 9 equal to 2 times 4 plus 1. Next division, 4 equal to 4 times 1 plus 0. Then we cross out the last row. Start from the second last row here. For each row here, get a remainder by itself. For each row here, get a remainder by itself. 1 equal to 9 minus 2 times 4. Next equation, 4 equal to 13 minus 1 times 9. Next equation, 9 equal to 61 minus 4 times 13. Then start from the last equation, try to substitute backward. We have 1 equal to 9 minus 2 times 4. Replace number 4 with the previous row. So 1 equal to 9 minus 2 times 4 is 13 minus 1 times 9. Then distribute 2. Distribute negative 2. We have 9 minus 2 times 13 plus 2 times 9. Then combine like terms. 1 9 plus 2 9 is 3 9. 1 9 plus 2 9 is 3 9. We have 1 equal to 3 times 9 minus 2 times 13. Next, try to replace 9 with the first row. Replace 9 with the first row. 9 is 61 minus 4 times 13 minus 2 times 13. Then distribute 3. If we distribute 3, we have 3 times 61 minus 12 times 13. 3 times 4 is 12. Minus 2 times 13. Then combine like terms. Negative 2 times 13 plus negative 2 times 13 is negative 14 times 13. Now here I write number 1 as a linear combination of A and M. I write 1 as a linear combination of A and M. Then the inverse of A. Inverse of A, here A is 13. The inverse of A is the number in front of A. So inverse of 13 is negative 14. So inverse of 13. Inverse of 13 is negative 14 mod 61. So inverse of 13 is negative 14 mod 61. In general, we try to use the least non-negative residue here. Since negative 14 is less than 61, I can add 61 to make it positive. Since negative 14 is less than 61, I can add 61 here to make it positive. If I add 61 here, I get positive 47. So inverse of 13 is 47. Inverse of 13 mod 61 is 47. So that's an answer. That's the inverse of 13 mod 61. 47 is the inverse of 13 mod 61. If we want to check an answer, we can take 47 times 13, then divide by 61. Take 47 times 13 divided by 61. If the remainder is 1, then 47 is the inverse of 13. If take 47 times 13 and divide by 61, remainder is 1. That means 47 is the inverse of 13 mod 61. So let's check. If I multiply 47 by 13, take 47 times 13. Here I use my calculator. 47 times 13 is 611. Then take 611 divided by 61. If the remainder is 1, then 47 is inverse of 13 mod 61. take 11 divided by 61. 61 goes into 61 one times. (61 minus 61 is 0. Bring 1 down. 61 goes into 1 0 times. 0 times 61 is 61. 0 times 61 is 0. 1 minus 0 is 1. Remainder is 1. So that means 47 is inverse of 13. Mark 61.